Alright, so in this video we go over the chapter 10, which is linear regression and the test for correlation. So as the title said, well, we're going to work with linear models. Before doing the statistical part, we're going to review what linear equations are. Typically we write them in the form y equals mx plus b, where m is the slope, which tells us the rise over run ratio, and b is the y value in which the straight line crosses the y-axis. To find the slope, well, we know the formula y2 minus y1 over x2 minus x1 given the 2 points. So let's just do a brief example to just to refresh a little bit of our minds for linear equations. So well, we're asked to find the equation of the line that passes through the points -1, -5, and 2, 1. If you want to label these numbers, might as well, why not? x1, y1, x2, and y2. Okay. So to find the equation of a line, we need 2 pieces of information, 1 point and the slope. In this case, we don't know the slope. Okay, so we need to calculate the slope first. M equals y2 minus y1 over x2 minus x1. In this case, well, y2 minus y1, that's y minus -5 divided by the difference of the x's, x2 minus x1, that is 2 minus -2. And be careful here when subtracting these negatives, because minus minus, actually we can refer to the smile rule. Have you heard of that? Well, minus times minus, do you see the smile? That means smile be positive. So 1 plus 5 over 2, actually this is a 1 not a 2, 2 plus 1. So this is 6 over 3, which equals to 2. And then we're going to use the point slope form. Y minus y1 equals m times x minus x1 to use the slope and any of the points to get the equation of a line. Well, in this case, does it matter which point do we choose to get the equation? No, it doesn't matter. However, I'm going to use the second point instead of the first one, because this way I don't have to deal with too many negative signs. But of course, if you want to do it on your own for the first point, well, that's up to you. You should get the same answer, by the way. So y minus y1, y, well, that's a 1. M, which is 2 times x minus x1, well, in this case 2. That is y minus 1 equals 2x minus 4. And add 1 to both sides to get y equals 2x minus 3. Alright, so what are we going to do here? Well, let's graph the line. Let's graph the equation of this line. The points are -1, -5, and the other point is 2, 1. Okay, so in this case what we're going to do is we are going to connect the dots here. The slope is rise over run 2, and just draw the equation of the line. Alright, now what is this relevant to what we are going to do for the rest of the chapter? Well, in this case, these points that I am highlighting pretty much in here, we say, because all these points are perfectly aligned to the graph described by this equation. In this case, we say we have 100% correlation. Well, what is that? Because now, moving on to the statistical part of this, well, we are going to collect data and we're going to have a bunch of points. We're going to have what we know as a scatter plot. So, and then from there, well, we are going to identify whether the points kind of follow a linear trend or not. All right, so that's the next page. So correlation, let's have a look at that. Well, a correlation exists between two variables when one of them is related to the other in some way. Okay, so a correlation measures both the strength and the direction of the relationship between the two variables. So, and the formula to calculate R, which is the coefficient of correlation, is this big formula. Well, what is this big formula? So the way we work with this formula, well, actually, we're not going to work with this formula. We're going to make it way easier than that. We are going to be given some order pairs and test whether we have a linear correlation. So this is n, which is the number of ordered pairs, times the sum of the products of x, y minus the sum of the x's times the sum of the y's. Well, this is already a huge task. And then look at this. So it's important to know where is this coming from. It's important. However, we're not going to do it this way. Now, some of the characteristics of R, the correlation coefficient, that's R, lowercase r, those values range between -1 and +1. Positive R indicates positive relationship between the two variables, and a negative R indicates a negative relationship between the two variables. All right, you know, for the positive correlation, as x increases, y increases. You know, for example, the length of employment, you know, it's and salary exhibit a positive correlation because the more you work, the more money you make, as opposed to the negative relationship in which the age of a car, well, after a while, a car loses its values. You know, a new car is really expensive, but over the years, you know, 5 years, 10 years, that car starts losing its value, and it's way cheaper than it actually was. Okay, so to give you, well, the bigger picture of this, well, so we are going to collect a lot of points, and it's going to look like this. All right. So in this case, well, we have some positive correlation between x and y, and in this case, we are going to have a line, well, not a horizontal line, a straight line that in a way fits most of the points. It may not be a very, very strong correlation, but well, it has the look of linearity. For letter B, well, the points are closer, are not that scattered as they were here. In this case, are closer to the line that best fits. So that's why we have some strong positive correlation. What about this one? Perfect positive correlation. This is one example of 100% correlation. This may not be 100%, of course. It might be 93, 92, I don't know. It's not part of what we want to do in this case. Well, and in this case, well, we have some sort of a negative correlation. But in this case, it may not be very strong because look at how the points are very scattered. They're not too close to the line, as opposed to the following case. In this case, in this graph, I mean, so all the points are closer, are very closer to the line that best fits. And in this case, we have a perfect correlation, perfect negative, but in this case, negative as opposed to positive. What about points in this case? Well, in this case, we cannot fit these points in a line. And in this case, well, as we're going to see later in the video, the best estimate for this will be the mean of the y value, some sort of a horizontal line that is right in the middle between the lowest and the highest. All right, but we will discuss that later. And in this case, of course, can we go beyond linear regression? Of course, there's like a quadratic regression. There's even exponential regression, logarithmic regression, polynomial regression, or even trigonometric regression. However, in this course, we are going to limit to look only at a linear regression. Okay, so let's construct scatter plots and find the line of best fit and the coefficient correlation R. So let's graph the points that we have here. So we're going to plot the point 0, 1. 0, 1. I can use a different color. 0, 1, 1, 2, no, 0, 1, 1, 2, not this one. Let's erase that one. 1, 2, and then 2, 4, and 3, 4 as well, and 4, 5, and 5, 6, and 6, 7, and 7, 7. As you can see, all these points, they seem to have some sort of linear trend, right? Okay, I'm just drawing the line that best fits this all these points. So does it seem to be a linear relationship between x and y? Well, the answer to this is yes. What is the value of r? Well, the value of r is r equals 0.979. And what is the equation of the line that best fits the data? Well, in this case, y equals to 1.417 plus 0.881x. Well, where did I get this 0.979 and this point in this equation of the line? Well, there is a separate handout on the model where we are covering this, so you can do the scatter plot on the calculator and get this information on the calculator. If you want to pause the video and check out that additional handout, go through the process and corroborate this data for it. Okay, once you're done, you might want to go back to the next topic. All right, so is R strong enough to merit a relation? Well, as you can see here, as we went over here in the different cases, there's a very strong, actually a perfect correlation. Here we have some sort of a strong but not perfect, yet it is a linear correlation. Here it's even weaker. But there are limits. There are limitations to determine whether we have a linear correlation, and those limitations are dictated by the value of R. So in this case, we are going to use a table of standard values, like the Z-scores, that we use critical values, right? So we're going to use a table that a table of values called table A6. And this is going to be some sort of a hypothesis testing. All we're going to do here is compare numbers. If R, which is the R that we obtain in our statistic value, is more than the critical value from the chart, well, then there is a relation between the variables. Otherwise, well, there is no relation between the variables. I mean, right now it looks like a lot of text here. So let's do an example to see what about it. All right. So let's see. We have this example right here. The data below describes the relationship between number of hours studied, which is the X value, and GPA, which is the Y value. So we're going to answer a number of questions here related to this example. All right, before moving on, so in this case, X and Y have a special name. Number of hours, which is X is called the explanatory variable, while the Y value, in this case GPA, it's called the response variable. Okay, so yes, I mean, depending on, so we are getting certain GPA. What's explaining my GPA of 3.1 of 3.9? Well, it's explained by the fact that I studied 10 hours. How come did I get a GPA of 3.5? Well, that's the response of getting a GPA of Y is explained by studying 9 hours, right? What is the equation of the line? Well, so this time I'm going to show you real quick about how to do it in the calculator. So I already have my data set. So we're going to go to Stat, Edit, and I already have my data stored in L1 and L2. L1, it's all the data of the X values, and L2 is going to be all the Y values. You might want to make note of that. L1, L2. Okay. What is the equation of the line that best fits the data? Well, I'm going to quit. Then I'm going to do stat, test, and I'm going to do linrect t-test. Well, in this case, well, I have L3 and L4 because that's for my second data. Be sure to do second and then L1 and for the X list, and second L2 for the Y list. Everything else, just ignore it. Just frequency, I don't know what that is 1. This, just leave it as equal to 0. We're not going to do any of that. Reg eq, just leave it. And calculate. And you're going to get all this. So the equation is of the form of y equals a plus bx. Be careful, because at the beginning of the video when we reviewed equations of lines, we had it in the other order, mx plus b, or ax plus b, if you will. In this case, when getting a and b, a is the independent term and b is the slope. So in this case, the equation of the line that best fits the data, that's y equals a plus bx in this format, which is 1.138 plus 0.257x. Okay, so that's the equation of the line that we can potentially use to estimate other values. What is the value of r? Well, going back to the calculator, keep scrolling down. And in this case, I would like to make note of both r and r squared. We're going to look at that. Well, r squared, we can look at r squared afterwards. Okay, so for now, let's look for r, which in this case is to 3 decimal places, by the way, 0.990. This means that there is a 99% correlation. All right. Now, let the significance level be alpha equals 0.05. Is there a significant correlation between these two variables? Well, so in this case, we are going to do some sort of a hypothesis testing. So the null hypothesis states that we do not have enough evidence with this data to say that there is no correlation. The alternative hypothesis would be that there is actually a relationship between number of hours studied and GPA obtained. So this is what we are going to do. So we're going to draw a number line. There's going to be the 0 right in the middle, as usual. But in this case, we need to find what n is. N is the number of order pairs in the data set. Like in this case, we have 1, 2, 3, 4, 5, 6, 7 order pairs. So n equals 7 with alpha equals 0.05. And where are we going to get these critical values? Well, there is another table that we're going to use. It's also given separately. Well, these are critical values for the Pearson correlation coefficient. Actually, that's the actual name of this coefficient. You know, like we use critical C-scores, critical T-scores, and eventually we're going to use critical chi-square scores and critical F-scores. These are going to be critical R-scores or critical Pearson correlation coefficients. So in this case, we have n equals to 7, alpha equals to 0.05. So we're going to go to n equals to 7, which is right here. And then these two columns are for alpha 0.05 and alpha 0.01. So we're going to go alpha 0.05, which in this case is 0.754. All right. So this is the critical value, RC, if you want to call it RC for critical, 0.754. However, in this case, keep in mind that correlation could be negative. So that's why we are going to have the other side of the test. RC equal to negative 0.754. All right. What is this going to be? Well, if our R falls within the green, either of the green regions, then we are going to have a correlation between hours studied and GPA. Otherwise, the one in the middle, well, that's going to be the red region. In this case, it wouldn't be a correlation. So what are we going to do? Well, what is our test statistic? R equals 0.990 or 0.99. That number falls somewhere here. R equals 0.990. It's indeed greater than the critical value. Or if it were negative, it would be even less than the negative. But in this case, we're looking at the positive side. Now, based on the result obtained in part C, can the linear model be used to estimate other values? Yes, because there is a correlation. All right, there is a correlation, therefore we can use this equation of the line to estimate other values. So for example, what is the best GPA estimate for someone who studied 3 hours? Well, all we have to do is plug in 3 wherever we see the letter X, which is here, and simplify. So 1.138 plus 0.258 times 3. If you put this in the calculator, you should get 1.9. Let's round GPAs to 1 decimal place. Letter F. What is the best GPA estimate for someone who studied 5 hours? Well, all we do again is plug in 5 where it corresponds for the X and run it to 2 decimal places. 2.4 is the best estimate. All right. Letter G. What's the best estimate for someone who studied 8 hours? Well, 1.138 plus 0.258 times 8. Putting this in the calculator, rounding to 1 decimal place, 3.2 GPA. All right. The coefficient of determination, R squared. So in this, sorry about that. In this case, we're going to look not only at R, but also R squared, which I already showed you in the calculator, its value. We're going to look at that again. So there's 2 differences. In this case, R is the coefficient of correlation that tells us the percentage of how percentage-wise how good the linear correlation is. The coefficient of determination, r squared, is a measure of the proportion of variation in the response variable y, that is, and the explanatory variable x. We're going to interpret this in a very, very short paragraph for this example. So, interpret the coefficient of variation for the situation in example 3. All right, going back to the calculator. So we had that r squared is 0.98. All right, 0.98. We're going to round that to 0.98. Actually, 0.98. Yeah, let me just 0.98. That's r squared. Let's change this to percent. That's 98%. So we need to write a brief paragraph interpreting this result. So what this means is that 98% of the variation in the GPA can be associated with the variation in the hours of study. But now this is 98%, so there is some remaining 2%. So the other 2% of variation is associated with other factors. Or even sampling errors. Again, keep in mind that when we're taking samples, well, sometimes a sample may not be representative of what we want to study, so, but in this case, well, we got a 98%, so this is really good. This is really good for our purpose. Now, what happens if R does not satisfy the requirements of table A6 to be a correlation between the two variables? Well, in this case, and I have actually bold case it. It's a bold case. Well, the linear model cannot be used to predict or estimate other values. So that's the caveat here. So the best estimate will be the sample mean of the y variable. In other words, one var stats for the y variable. So we're going to look at an example that actually depicts this very, very nicely. Well, so the data below represents the relationship between cats' weights and their paw sizes. So x is, all the x's are the cats' weights and all the y's are their paw sizes. What is the equation of the line that best fits? Well, again, keep in mind to put this in your L1 and L2. All right, so, well, however, in my case, in my calculator, because I already had everything in my calculator, I didn't want to erase L1 and L2. So in this case, in my case, L3 is going to be my x, and L4 is going to be my y value. So I'm going to, let me quit. Well, actually, you don't need to quit. Stat. We're going to do tests. and we're going to go to linear t-test. And I'm going to change L1 and L2 for L3 and L4 respectively. L3 and L4. Alright, then I'm going to go down and calculate that part. So this is what we obtain, A and B. Alright, so y equals A plus bx, which is in this case 6.644 plus 0.090x. Alright, so that's the equation of the line. The value for r, if you look at the value for r, is really lame. R equals 0.117 174. All right, that means, what does that mean? This means only 17.4% of correlation. So this is really bad data. That means if we do the scatter plot for this, we're gonna get data that will be really scattered. All right, so let's do the statistical test anyway. So at the significance level of alpha equals 0.05, is there a significant correlation between these two variables? Well, we need to determine what n is. In this case, n is the number of ordered pairs. 1, 2, 3, 4, 5, 6, 7, 8, and 9. N equals 9 with alpha equals 0.05. So in this case, we're going to look at the table. Let's do our number line, the 0 in the middle, the positive critical value, the negative critical value. So, well, in this case, n equals 9. I'm going to go through the n equals 9, alpha 0.05. That's 0.666. All right. So R critical 0.666, and R critical on the other hand negative 0.666. All right. It turns out that our actual correlation coefficient is really low. It actually falls in the no correlation region, in the red region rather than in the green region, as we can tell here. So R is only 0.174. So in this case, based on the result in part C, can we use a linear model to estimate other values? Unfortunately, no, because there is no correlation. Well, what is the best paw size estimate for a cat that weighs 11 pounds? So in this case, we cannot use the linear model, as we can see here. Well, we're gonna find the mean, the sample mean of the y variable. So what are we going to do here? One var stats for the column, for the L in your calculator that contains your y values. So let's calculate that. So again, let's review the data here. So the y values for the second situation are here in L4. All right, so I'm going to quit and I'm going to do stat calc 1 var stats for L4. Oh, it's already there because I did it before doing the video. Frequently just leave it blank and calculate. And we are interested in the x bar. That is, well, of course, for our purpose would be y bar, but the calculator doesn't call it x. The calculator by default uses the x letter. So in this case, let me call this y bar, which is 7.4. All right, now let's see what about this. Well, so let's do the scatter plot. So let's do second stat plot. Well, notice it's off. I need this to be on. And I need to do a scatter plot, which is the first image. And I'm going to do the scatter plot between L3 and L4. Of course, if you had this data in L1 and L2, we would have used L1 and L2 respectively. All right. So I'm going to graph. I'm going to click graph and see how scattered the data is. Well, let me actually erase this curve right here. Graph. I only want to see the scatter plot. And in this case, I'm going to do zoom and zoom stat to see only the part of the graph that contains my data set. And actually, if you can see, there is no linear relation. The data, it's actually just scattered. How? Well, remember the case that we had here, this one right there. Well, very, very scattered data. The mean, it's only this line. You know, the actual mean of the y values. All right. So now, well, as one more piece of information here is to interpret the coefficient of a variation. And the coefficient of variation, again, okay, let me do the test, the linear recti test to retrieve that value again. So r squared for this situation is only 0.03. All right. So r squared equals 0.03. Okay, how do we interpret the coefficient of variation? Well, we're going to write a brief paragraph in which we are going to say that's 3%. So 3% of the variation in the pause sizes can be associated with the variation in the cat's weight. All right. Well, in this case, if only 3% of the variation can be associated, the remaining 97%. See how this 97% of the variation is associated with other factors or even sampling error. All right. Well, if we analyze this situation, well, what could it be wrong with sampling, with getting this data? Well, most likely when obtaining this raw data, many different cats of many different breeds were sampled, you know, and there's many breeds that do not really or do not necessarily share any characteristics. So most likely, if we were given data from the same breed of cats, maybe we would have obtained a better correlation. But in this case, taking a sample of just random cats, well, different breeds, different characteristics, it's going to give us a really, really low correlation. All right, so this is the end of this video. I'll see you in the next one.